So here we go with the last section. In problem 41 here, in the fifth series, that would be down here, 1, 2, 3, 4, 5. Their series is horizontal, so you're going number 5 here. Okay, you go 5s. Then after 5s, it's followed by 4d. So the next 10 elements, key word here was 10 elements, because that tells you that's probably the D sublevel block, since the D sublevel holds 10 electrons. So 5s is followed by 4d, and that would be D, choice D. Okay, the orbitals in the dot notation of aluminum. Dot notations always include either S or S and P, but never D, because D can't be in the outer shell, given what I just showed you, that you 5s and 4d. Up here it was 4s followed by 3d, so you'll never see a D in the outer shell. So aluminum's configuration: 1s2, 2s2, 2p6, 3s2, 3p1 makes 13 electrons. Aluminum has 13 electrons. These are the electrons that are in the outer shell. What are the sublevels? S and P. Now, how many third electrons, energy level electrons, are present in holmium? Holmium is element HO, and it's number 67. It's in the 4F sublevel block. So if I wrote the electron configuration out to holmium, I'll just show you. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. How many did I say it has? It has 67. Okay, at the end of 5p6, I'm up to 54. So after 5p comes 6s, 2, and then it'd be 4f. So how many do I have here? I was 54, there's 56, and I'm going to 67, so I need 11 more. And that would be the configuration. So how many third energy level electrons are there? Well, the 3d, the 3d, and the 3p, and the 3s. So that's 18. So 18 is not there, so best answer, E. All right, you got 4 quantum numbers, N, L, M, and S. If I want to describe a sublevel, I need to know what energy level it's in, and I need to know if it's S, P, D, or F. So that's N and L. We don't need M to describe the sublevel. We don't need S to describe the sublevel. So the answer is just 2. And if 2 electrons are in the same sublevel, then they've got to have the same value of N and the same value of L. Because N tells the energy level, and L tells you the sublevel. They could have the same M value in common, but they don't have to. That's why I said must. Okay, now we go down to these matching ones. 7 values of M, that means 7 orbitals. So what up here has 7 orbitals? That would be A. Inversely proportional to energy. So we had a couple of equations, I'll write them down here. Energy is equal to H times frequency, and C is equal to wavelength times frequency. Wavelength times frequency. Wavelength here, frequency here. Now I could, watch this, I could divide both sides by wavelength. And if I did divide both sides by wavelength would cancel on this side, and I would have this equation, nu, right here, is the same thing as C divided by wavelength. Then I could take this and plug it in right there. So I'd have a new equation, E is equal to H times C over wavelength. Now it might be easier to see that the energy is inversely proportional to the wavelength, because these are both constant. So if this number gets bigger, then this number has to get smaller. Or if this number gets smaller, this number is going to have to get bigger, since the wavelength. If you don't believe me, try it. Just put, the constant will make us 8. All right, so if I made this 2, then this would have to be 4. But then if I had 8 and I made the bottom get bigger, that's 4. What's 8 divided by 4? 2. So you see how this number got bigger, this number got smaller. Inversely proportional. So the answer there is wavelength. Okay, energy is directly proportional to frequency. That's this equation. So what does this equation apply to? Applies to photons. Hund's rule says that you have to put electrons into orbitals one at a time. So if you draw the dot diagram for oxygen, you'd have 6 in the outer shell. Ask yourself, do I know why there are 6 in the outer shell? Oxygen's in the 6th column. So there's 2, 3, 4, 5, 6. So I had to go singles before I paired up. That's Hund's rule. All right, this one, a joule second squared per kilogram meter. I'll go ahead and show you this. So a joule is a Newton meter. So I'm going to write that as Newton meter second squared over a kilogram meter. Now, why is a joule a Newton meter? Because a joule is a unit of energy. Energy and work have the same units. So we would say energy is the ability to do work. And work is force times distance. Newtons are force, meters are distance, force times distance. So a Newton meter is the same thing as a joule. Notice immediately what happens. Meters cancel. So now I've got Newton second squared over kilograms. But a Newton can be written, since Newton is a force, and force is mass times acceleration, it's a kilogram meter per second squared. So that's the same thing as a Newton. Multiply by second squared, because Newton second squared, what I had right here, Newton, second squared. On the bottom you got kilograms. Now what happens? That doesn't happen. This happens. Second squareds cancel. Kilograms now would cancel. So what do you have left? All right, so the answer is wavelength, measured in meters. All righty, here we go. Now, on 51, remember that? Okay, which has the higher energy? Okay, so that's high energy. And this is low energy. So what's listed? Oh, orange is listed. So the lowest energy would be C. The longest wavelength, would that have a high energy or a low energy? Remember wavelength, that was that relationship. C is equal to wavelength times frequency. So if this number gets bigger, that number has to get smaller because this is constant. If you don't believe me, if this was 2, and the constant's 8 again, just making up a number. If that's 2, what's this equal? 4, because 2 times 4 is 8. But if this gets bigger, 4 times what equals 8? 2. So as this gets bigger, that gets smaller. Right? Inversely proportional. Right. So low energy would be a what for wavelength? It'd be bigger, wouldn't it? So which one of these has the longest wavelength? Going with the lowest energy. So that also is orange. All right, the most quantum numbers shared between 2 electrons in an atom is 3. That's the Pauli exclusion principle. It says that no 2 electrons can have the same 4 quantum numbers. Cycles per second is another word for frequency. And the result of moving away from the ground state is referring to this. So you got a nucleus, you got the first energy level, you got the second energy level, you got the third energy level, you got the fourth energy level. You got an electron sitting here. If the electron gains energy, he moves away from the nucleus. So he goes out here like that, or maybe out here like this. But he can't stay there, he comes back down. So if we measure the energy that it takes to move away from the nucleus, did the electron absorb energy or release energy as he moves away from the nucleus? He absorbed energy, so that's the absorption spectrum. And that's the end of the test review. So I hope this makes sense. And there you go, I'll post these, and then I will have kept my promise to make this happen.